well, thank you all for coming. I'd like to introduce Lynde. He has been working in the Thin Films Lab this past year on Janus particles, and he's taken it in a new direction. If you haven't heard about Janus particles, it's relatively new. It first shows up in about 1988 publications, but they don't take off until about 2003, 2005. And if you survey the literature, you don't see much in the way of applications, maybe less than 10% of all articles that are published on applications. So what Ben has been doing is a possible application using the Janus particles. I'm not going to say a lot. I'm going to let him tell you about his research. Okay?
Thank you, sir. Thank you all for coming. I have actually been very lucky to be given this opportunity. It's my understanding that research that is this open-ended and free for me to pursue, taking what direction I want, is actually pretty rare. I was lucky enough, being that I have two real interests here at VMI. I'm a physics major and a concentration in molecular biology and biochemistry, and I was able to kind of piece both those sides of my academic career together. And it was very nice to see it come together so well, and without any further ado, we'll go ahead and get started. So, what was kind of the purpose of this? Well, it started out as more of a physics-oriented project. The first semester, we were mainly studying what kind of properties Janus particles had, how they could be useful, and the rotational dynamics. So that's more the mathematical side, and we'll get into that with theory. The second semester, seeing that we were successful, we could kind of use the Janus particles as we intended the first semester. We wanted to use this in some sort of biomedical application. So the kind of big idea was to simulate human cells with Paramecium and use the Janus particles as some sort of therapeutics. Again, I'll get into that in theory. And overall, I really just gained a lot of experience with different laboratory equipment, different types of experimentation, and a lot of different programming as well, stuff that I really did not think that I would get from this project. So to start, Janus particles, what are Janus particles? Well, the name comes from the Roman god Janus, which is really just a god of two faces. And that's really what they're known for, is these particles have two faces, and so you can use the properties of both. So for instance, one of the more famous applications is they actually created a film of these that were just like this. So you see half coat on one side, this one happened to be similar to ours with a magnetic material, and half coat on the other with some sort of translucent material, some sort of plastic or glass or something like that. So this film, polarized, how you see here, would let through about 50% of the light, because if this side was transparent, the light would go through. But then you could use a magnetic field to indirectly change the orientation of these. So maybe it was split horizontally. The A side was on top, and it blocked most of the light. So what you could actually do is indirectly control these particles to change the polarization of some film. So that's just one of the applications. Ours is similar, using the magnetics of one side and the transparency of another. So we'll get to that. But overall, what you need to know is that the benefits of using these is you can indirectly control them. So the mathematical part we were talking about, rotational dynamics. We had this idea that we could coat half of these particles with a magnetic material, some sort of ferromagnetic material, nickel or cobalt, that would respond in a magnetic field. If we could get them to respond enough that they could follow a rotating magnet, perhaps we could get these Janus particles to spin round and round and round and round. The purpose of this we'll get to later, but the first step was, can we get these to spin? Well, we knew these were going to be the mathematical equations that govern this dynamic. So in looking at these, we said, okay, well, if we're going to be able to tell, the easiest thing we should do is use a larger particle first. So you see here this 4.4 millimeter particles. We coated those first, so we could actually study just the properties of a Janus particle and say, okay, well, if it's large enough to see, will it follow the magnet? Can we progress and follow? So how do we do that? Well, first of all, we had to go to the drawing board, and so we used the modern drawing board, which is really programming, SolidWorks. And we made this model. This was actually done by my lab partner at the time, Patrick Pyatt, and gave this to, so we made this model and gave this to Cronenberg and used it as 3D printer. So we printed out two masks, so we could kind of sandwich the particles in between these, giving us the coating exactly where we wanted it. So the particles would lie in these holes, depending on what size we wanted the cap or the coating. And then we would tie off the masks on these ends here and put them right here in the evaporator. We'll get to that later. So in this evaporator, really attached to the side, is this thickness monitor. This little black box is wired up to here. So when the nickel, which is our coating, we actually would evaporate onto the bottom. So when we take this metal, turn it into a liquid and quickly into a gas to go onto the bottom of the part and give it a coating, it also coated the bottom of this here, which is a small quartz crystal. So this crystal has a known vibration rate, and when the nickel ends up on it, then it actually changes the vibration rate due to the weight. So this black box would calculate that and say, all right, well, if the weight has changed this much, then you must have a thickness coating of 140 nanometers, for instance. So this would be able to tell us how thick the coating was. And then all of this together would go inside this evaporator. This evaporator actually is an incredibly impressive piece of machinery. This blue box was able to contain all of this that you see here. This is where we would put these small chunks of nickel. So we'd have about 1 millimeter across little nuggets of nickel that would go in here. And then this whole thing with the mask, the crystal to tell the thickness, and the particle inside the mask would go inside the bell jar, which is this. The machine would pump out about, it will pump it to 10 to the -6 torr, which is extremely low pressure. So for those of you familiar with lots of physical properties of materials or some sort of chemistry, that actually changes the melting point. So it brings the melting point down, which meant we didn't have to get this nickel quite as hot to evaporate. So that's what I'll show you here. It's a pretty fascinating process because you'll see as the pressure goes down, we'll actually start pumping a current through here, about 50 to 70 amps, which is quite a lot. 10 amps is enough to kill a person. And so this will go white hot and actually start to melt the metal. So what you're seeing over here, this hand, is zeroing the thickness monitor. So right now it's 0, and it'll tell us what the thickness actually is. So you can see the current pumping through this small wire basket. And it'll get it so hot that it evaporates the nickel onto the actual particle. So that was the fabrication process. And upon finding that successful, we were able to move on to building some sort of apparatus to test it. So we said, all right, we need a rotating magnet. So we need these, what you will see here, these black sides. We need rotating magnets. We need to be able to control it. So we can control the actual rate of rotation. We need a way to monitor it. This setup, although it looks kind of jury-rigged, actually worked very well. What you'll see here in the middle, this is the particle itself in a test tube. So we put a little bit of DI water in there just to prevent any friction. And the whole setup is turned by this small red camcorder motor. So this is attached to the power output here, giving us a very fine control over just how fast this is going to be by how much voltage we would put out. So we control just how fast this spins, and it rotates around the particle. And then, luckily, we have this very nice vernier software that we could track the velocity and acceleration of the magnets. So, if you look back here, this is that CCD camera that we use to actually observe it. It looks right down the axis of rotation. So this is what you'll see here. If you watch, it's going to be hard to track with this laser. You can actually see a small dark spot that rotates around. So this is what we were looking for, just really the rotation itself. But we didn't actually have the technology to tell just how fast it was rotating at a time just by looking at this. It was very difficult to actually mark a spot on it and tell the rotation. So we just made sure that in watching this, that it would not lose phase with the magnets. So we were looking to make sure that the speed of the particle spinning matched the speed of the external magnets. So that's what we were looking for. We noticed as we picked the speed up, it would actually fall out of phase and lose that dynamic. So what we learned from that initial experiment was, yes, we can fabricate Janus particles. Yes, we can get them to rotate. On the condition that we keep it at a low rate of spin, so around 1 radians per second. So we knew from here we had to take our project that would spin at 1 radians per second. Another important note is that, so this is done by Big Hawk. This is not our figure. This is done by a professional, and we use this as kind of saying, okay, well, we noticed a similar trend in ours. We're on the right track. But an important note about his is his spheres were 7 micrometers. So that's more on what we were looking to do down the line. But we weren't quite there yet. But it did give us kind of a sign of hope that he could actually get it to work with these. Not to mention, his magnetic field is 0.006 Tesla. For reference, that's actually 6 times the strength of the Earth's magnetic field, which is enough to get a compass to spin anywhere. So it is impressive. But our actual magnetic field between those 2 little neodymium magnets you saw there was 0.5 Tesla. So it's much, much larger. So going into the second half, we actually had a lot of hope that with a much stronger magnetic field and a lower rate of spin, that we would be able to keep them in phase. So we went to the next semester with a lot of confidence. So the next semester, this is the biomedical application. This is the part where I had to kind of marry those 2 sides of my academic career. And the idea that came to mind, well, the idea that we kind of put this towards, was that if you can somehow get these particles to a group of malignant cells, to a tumor, something else that is causing damage to the body, then perhaps once the cells are accumulated on the tumor, you could use an external magnet, like how we've done on our setup, and manage to spin the particles while they're inside the body. This would cause this would destroy the cells through heat, through shredding, some sort of way. We want to localize destruction, some sort of alternative to chemo or something that would nuke the whole body, like maybe some sort of better therapeutic. So in researching this, I found that there was some good hope that nanoparticles could end up accumulating in a tumor. There's plenty of research showing that nanoparticles in the range of 50 to 300 nanometers, which are considered small, so ours are 1,000 nanometers, which is not completely out of range, would be drawn to the tumor in something we call the EPR effect. Now, the only problem with this, as I'll talk about later, is that also 5% of this dose made it to the tumor, but the rest of it ends up in the spleen and liver, which is something to be explored later. Now, the spleen and liver are meant to filter out stuff like this. So it's not unheard of that it wouldn't be a problem, but it's also unexplored, especially with our particles. But these gentlemen here, or ladies, I'm not sure, actually did use nanoparticles. And they found that based on the molecular weight, within the range of 15,000 to 70,000 grams per mole, they would accumulate effectively on the tumor using that EPR effect that I talked about earlier. So I calculated the actual molecular mass of our Janus particle using what we got from that thickness monitor. So the stuff we were talking about earlier, I found it was 140 nanometer thickness on average, and the details from the scanning electron microscope in our lab to tell us just what elements were in the actual coating. So using those 2 things, I calculated the molecular mass to be around 3,000 or 33,000 grams per mole, which is perfect because it puts us in great shape for that tumor-tropic movement, so moving towards the tumor. So the theory was working out. We had some positivity going into the actual observation. So I have one more note on the theory actually before we go into the observation was what would actually destroy these. In the process of this, we thought originally it was going to be the heat. So we thought if we spun these particles next to the tumor fast enough, it would generate enough heat to kind of cook that one part of the body from the inside out. So we could cook these cells using just magnets from the outside. But in making these, we found that using 1 micron nanoparticles with 140 nanometer coating, it actually creates a kind of lip that could shred. So I made these models in SolidWorks to show that instead of that kind of A-B slide you saw in the beginning theory slide, where it looks like they're both identical sides, that this could actually create some sort of lip that could cause damage in itself. So the particles we used were anywhere from 1 micron across to 5 microns across with the same coating. So this is the kind of variety that we'd see just to make sure this size would be right for the paramecium. So we had a couple questions to answer. If we were going to figure out what was going to kill these paramecium by just saying, okay, well, we're going to take these paramecium, again, as a kind of substitute for a human cell. So we're going to use these paramecium and say, well, if we get them to actually ingest the particles, to eat the particles, and then spin them from the outside and see if we can destroy the paramecium from the inside out, like you might some sort of tumor, some sort of group of cells, then how are we going to make sure that it was the particles being spun by the magnet that actually did the damage? Well, we had to eliminate a couple things. So these are our main questions. First of all, do the paramecium even eat the particles? Do they ingest them at all? Second, do the particles alone kill them? Are they toxic? Is the nickel toxic? Is the shape toxic? Are they too large for the paramecium to handle? Third, can we even control these small particles from the outside with the magnet? 4, does the magnetic field itself kill the paramecium? So does exposure to a magnetic field somehow kill the paramecium? So, on to the observation. This is what we found. First of all, for the first question, you see here, this is kind of what the particles look like in the medium that the paramecium are in. So this one was one of the large ones, it was 5 microns. And then over here, we found another picture of the paramecium. This one was glued down by a cell glue that Colonel Bell has in his lab. So normally they're quite active, as you'll see later. But this one glued down, we looked at it, found a couple dots, and measured them with the software to see the actual diameter. We said, okay, these are about, or these are all like exactly 1 or exactly 2, exactly 3 microns across. So these are most likely our particles. We were pretty sure that they were actually inside the paramecium. But to make sure, we started using the actual fluorescence nature of the particles. So again, this is what I talked about is very unique about Janus particles, is we were taking advantage of that magnetic side, but also the other side of these particles is actually red. So we could excite that red color essentially in these in the other side of the particles, so we could see them by using what looks like kind of a glow-in-the-dark thing. So what were we testing for? Well, healthy paramecium. What says healthy paramecium? Cytoplasmic streaming. So this is what you'll see here, just kind of figure-8 motions. The nutrients go from the back to the front and to the back again. So you'll see that kind of slow motion. It basically looks like a flow inside the paramecium. So what we wanted to check for is, are our particles participating in this flow? Or are they blocking things? Are they harming the paramecium? So this right here is our particles. And you see the distinct dots here. The shape is easy, but this blur is actually a diffusion of the light when the particles are behind or in front of the focus. So what you'll see here is the particles moving around, although it's hard to tell with any reference if they're participating in the cytoplasmic stream. So what I want you to take note of is when I restart this video, you'll see these group of particles jump back slightly. And it's only going to be slightly because when the paramecium ingests these, they put them in these small vacuoles, so these bubbles inside the paramecium that move back and forth. And they're not going to move as fast as the rest of the nutrients in that kind of cytoplasmic flow back and forth. But if you look right about there, you'll see the particles jump back. So that's what we're looking for. We're saying, okay, in only a 10-second video, we could get some movement. So essentially we're saying, okay, they do move inside the paramecium. They are part of the cytoplasmic stream. Second of all, what also do they need to be able to do? Well, the paramecium need to be able to pass these naturally. It should come, even if they're not nutritious to the paramecium, it should come as they can eat them, they can move them around, and eventually pass them through without killing them. So how do we have proof of that? Well, again, by taking advantage of the fluorescence, we found a picture of one that was passing the particles through the back. So these vacuoles will line up against the cell wall and push anything that's not necessary out of the paramecium. And then a couple seconds later, we took the same picture and saw that our particles were also being passed out. So we're like, okay, great, the particles don't kill them. Good answer to question 2. Question 3, can we actually move these particles? So this is a very nice video. You'll see here, I have a magnet on the end of a screwdriver, so the same neodymium magnets, and I'll be moving it down and up and down again. You'll see the orientation of these actual particles change, where they'll start moving down this way and then back up again. And the more interesting part about this video is actually it's a really good job of answering question number 1, which is, do the paramecium eat them? So you'll see the particles start to move down. Okay. Let me see if I can get that video to actually work. Okay, so there's some technical difficulties. Really disappointing. It's actually one of the more interesting videos. Hopefully we can come back to it at the end. But we had a very rare shot. Well, I'll say just, I don't want to ruin it. Hopefully I can bring it back later. Either way, you'll have to take it on faith for this moment that we could move the particles with a magnet. So part 4. Could we actually kill the paramecium with a magnetic field alone? If they did die, is that what was going to do the damage? So to do this, we had to kind of run the entire experiment because we didn't have any way to visualize the paramecium, the particles together under a microscope. That whole rig, as you saw, did not fit under a microscope. We were just using that CCD camera that picked up the 4.4 millimeter particles and would definitely not pick up these. So we ran an experiment by setting up these different groups. And what you see here stands for paramecium, Janus particle, and B field, which is the magnetic field. So if it's red, then we did not include that particular mix. So this whole experiment was done where you have, first, this is just the paramecium to check if we got a bad sample, if the paramecium were dying on their own. Then the paramecium exposed to the magnetic field, as you see here. Well, that did not kill them as we thought. You know, paramecium should be able to stay in the magnetic field unless they have some sort of metal inside it, hopefully. So the paramecium and the Janus particles, we added them in about 10 minutes after and let them settle. Noticed again, no dead groups. And so that's what this DG stands for. Overall, this experiment, the final experiment we did here was very kind of qualitative because we did not have, again, the optics set up to count the paramecium. We could just take them out, put them under a different microscope that didn't have a picture set up, and just look for any dead paramecium. And so dead paramecium are actually easier to find than you think, because when they die, they start to swim in these small circles. The ATP in the actual cilia that move them starts to run out, and they move in these small little circles, and then other paramecium will group in beside them as they also die. So you'll get these small rotating groups. So that's what we were looking for. And so here is the actual experiment where you have the particles, the paramecium, and they were put in the magnetic field for 20 minutes here. And we noticed there was 3 to 5 dead groups. So there was something here. But after doing this, we also realized, well, are the particles killing them from the inside out, as we intended? Are they swelling? Are they killing them? Or is it that there's a bunch of particles in the bottom of this test tube, and when they're put in the rig, these particles are rising up and running around like shrapnel and destroying the paramecium like a blender? I mean, either way, there's cell damage, but we wanted to find out which one it was. So after a certain amount of time of settling, this here, where we said, okay, they've had time to ingest the Janus particles, the paramecium, they're going to eat them, we pulled out that top layer of paramecium and put them in a separate sample. Then we put that in the magnetic rig for 20 minutes and found 2 to 3 dead groups. So, overall, what do we find? We found that this concept is worth exploring. There is actually a connection between these, between ingesting the particles and introducing it to a magnetic field. So we found it does cause damage. Do we know if it causes damage through the actual blender effect, where they're in the bottom hitting everything, where they ingest them? No, not quite yet. That's going to be further work, as you'll see soon. What we did do is quite a bit in 2 semesters. We designed and built that testing apparatus, which is with precise control and good recording. Explored the different models for different models and modeling software to use that 3D printing mask. I don't need to read off the list, but we did quite a bit with these particles. Learned a lot about the particles themselves,